At this point, we've looked at a lot of different types of functions, and we've spent the last few sections looking over polynomials. We know how to find their zeros, we know how to find the end behavior of the polynomial, we know how to find the behavior around the zeros, and we know how to actually find those zeros if it's not in factored form using the rational root test, the conjugate zeros theorem, factor theorem, remainder theorem, and all of that. Now we're going to do something slightly different and look at a different type of function, rational functions. And as far as it goes, there's different ways to do this. For the purposes of this, since this is by video, I'm going to make two videos for this. In this first video, I'm just going to look at a couple of rational functions and go through how to actually solve them out and graph them step by step by step by step by step. And once you kind of get the idea, I'll make another video where I go through them quicker once I assume you kind of know the steps and know how it works. So, suppose we have a rational function that looks something like f of x equals x squared minus 1 all over x cubed minus 6x plus, we'll go minus 7. X cubed minus 6x squared minus 7x. We'll do that one right there. Okay, as far as it goes, first thing we do when dealing with these is factor them out as much as we possibly can. So in this case, the top is just a difference of squares, so that's x plus 1, x minus 1. On the bottom, there's a common x, so I can factor that out, and then I'll be left with x squared minus 6x minus 7, and then I can factor this quadratic, and I get x plus 1, x minus 1, all over x. Two numbers that multiply to negative 7 that add to negative 6. That's x minus 7, x plus 1. And now we see once it's in factored form, I can cancel out the x plus 1s. And in lowest terms, it's x minus 1 all over x times x minus 7. And now, our ultimate goal is to be able to graph this. And like I said, there's about 5, 6, 7 different things that we're going to use to actually find the graph of this. We're just going to run through them now before we get into it. So first, when we graph a rational function, there's a potential for there to be a hole in your graph. Holes in your graph occur at places where the function is undefined that get canceled out. So in this case, when we factor, the x plus 1s cancel out, which means my graph will have a hole at the 0 associated with x plus 1, which if we flip the sign, is x equal to negative 1. That's why we factor first to find any of the holes in our graph. Some graphs won't have holes, some will. Next up, after we look for holes, we look for vertical asymptotes. Vertical asymptotes occur where the function is undefined when it's in lowest terms. So in this case, here it is in lowest terms. The function is undefined when it's 0 in the denominator. We did this earlier in the semester talking about domains. So we find where it's 0 in the denominator. In this case, it'll be 0 at 0 and at 7. That will result in a vertical asymptote in my graph at 0 and 7. Next up, once we find the vertical asymptotes, find the zeros of the graph. The zeros of the graph occur where the function is 0, which in this case is where the numerator is 0. So we'll have a 0 at x equals 1, because on top we have x minus 1. So we'll have a 0 at x equals 1. Next up, a lot of times when graphing these, you don't really get enough information from some of the stuff we're going to find here. So we'll find one other thing. We'll find the y-intercept. Sometimes that helps give us an idea of what the graph looks like. To find the y-intercept, we make x 0. But in this case, if we plug in 0, we get undefined in the denominator, which just means For the y-intercept, we get none. Okay. Now, one other thing we can look for is a horizontal or oblique asymptote. Okay, and one thing to be in mind, we do not have a horizontal and an oblique asymptote. You have a horizontal or an oblique asymptote, one or the other. Don't try to find both, you can only get one. The word oblique, if you're confused, it just means like non-horizontal and non-vertical. So essentially, we're going to have some vertical asymptotes on our graph where it's undefined, and then we'll have some other asymptote, could be horizontal or it could be slightly slanted. Sometimes that's called a slant asymptote. And we're just going to have to figure that out using some algebraic tricks. I'll actually explain the rule really quickly. The short answer is, to find the horizontal or oblique asymptote, you look at the degrees. If the degree in the numerator is greater than the degree in the denominator, you get an oblique asymptote. If the degree in the numerator is less than the degree in the denominator, you get a horizontal asymptote at y equals 0. And if the degree in the numerator is equal to the degree in the denominator, you get a horizontal at the quotient of the leading coefficients. Okay, so essentially the idea is you take your rational function, you put it in lowest terms, and then you look at the degree. In our case right here, the degree of the numerator, the highest power of x, is degree equal to 1. In the denominator, we have two x's, which means my degree is equal to 2. So now the degree in the numerator is less than the degree in the denominator, so we should have a horizontal asymptote at y equals 0. We will look, like I said, I'm going to do several of these, and we will look at other ones where we get other types of asymptotes. Right now, we just have to kind of get an idea of what the rule says and how to apply it. So, since my degree in the numerator is less than the degree in the denominator, I have a horizontal asymptote at y equals 0. Now, in theory, I have enough information to graph this, so we'll see if we can do it. We should be able to fit it right in here. And now let's see, we fill in our information. We have a hole at x equals -1. Don't worry about that yet. We'll throw that on the graph at the end once we have everything else done. I have a vertical asymptote at 0 and 7. I know it's a little hard to see with the black and the purple together, but we have one at 0 and one at 7 right here. We have a 0 at x equals 1, which we'll say is right here. There's no y-intercept because I have a vertical asymptote there. And I have a horizontal asymptote at y equals 0, like that. That's all the information I have. Now I should be able to sketch it. And the problem here, much like with a lot of these, is that I don't really have a lot of information there. But what I do know is, for these vertical asymptotes, around the vertical asymptote, where the function is undefined, I have to either go up to infinity or down to negative infinity. So basically, around the asymptotes, I either go down like that, or I go up like that. I just need to figure out which. And there's some tricks we can do. Okay? And I can never touch a vertical asymptote. I can only approach infinity. I know some rules for polynomials, and they will apply here. But since I still don't seem to have a lot of information, there's one more trick I can use. Pick some other arbitrary point. For the sake of argument, since this is x equals to 1, I'm going to use x equal to 2. And I'm just going to see what the graph looks like at 2, what the function is. If I plug in 2 right here, I get 2 minus 1, which is 1, all over 2 times 2 minus 7. 2 minus 7 is negative 5. Negative 5 times 2 is negative 10. So I get negative 1/10. This doesn't really have to be accurate. All I really care about is at 2, I get negative 1/10, which we'll say is right there. And now I have enough information to graph it. Because now I know if I'm at this 0, I have to go through that point. Now I either go down or I go up. Since I have to approach infinity or negative infinity, if I want to approach infinity, I have to go back through the axis. But if I go through the axis, it gives me another 0, and I don't have any more zeros. So I can't go that way, which means I have to go down. On this side of the graph, to the left of this 0, again, here I actually bounce off the axis, or I cut through the axis, but that's based off of the degree of the degree of that 0. We remember that from graphing polynomials. X minus 1 is degree 1. Odd degree I cut through, so I'm going to go up. I can never go back down because that will give me another 0, so I go up to infinity. Now the only other trick we need is, what do I do on the other side of the asymptote? Essentially, if we look at this one first, on this side of the asymptote, I can either start up there or start down here, and I need to figure out which one. And the trick is actually the same as the polynomial trick. For polynomials, like this 0 right here, we said if the degree of the 0 is odd, we cut through the axis. If the degree is even, we bounce off. The same principle applies, but in a different way. We could say if the degree is odd, the sign switches around the 0, goes from negative to positive. If the degree is even and we bounced off, the sign stays the same. That's the other way of saying the rule. And that's actually the rule that applies for the asymptotes. To find the behavior around the asymptote, we say that's the asymptote for 0 right here. That's x to the 1, since there's no power listed. It's odd degree, so the sign has to switch around the asymptote, just like it switches around the 0. On this side of the asymptote, it's positive, so on this side, it has to be negative. And now, I have to come up. If I hit a 0, I would touch the axis, but I have no more zeros, which means I can't touch the axis. But that works because I have to approach my asymptote at 0, so I can just go and approach my asymptote. I never actually touch it because if I did, I give myself a 0. I just approach it. Now we do the same thing over here. I look at this asymptote, that's x minus 7, it's raised to the first. That's an odd degree, so the sign will switch, just like it did here. This is negative on the left, which means it's got to be positive on the right. So it's got to be up there. But if it's up there, it has to come down. It can never hit 0 again, because I've already found my zeros. So it just goes off and shoots towards my horizontal asymptote at 0. Now we've accounted for this, and that. The last thing we need, which is the thing I usually forget, is to throw my holes in there. And again, we don't have to be incredibly accurate here. At x equals negative 1, which we'll say is like right here, just draw a little hole. And then we're good to go, and we've done that. And if nothing else, at the beginning of the semester, we were just learning how to graph basic lines and solve basic equations. Now you can solve this stuff in just a few minutes. So, progress. You've learned a lot over the summer. This does take a while. It's been almost 15 minutes already just going through this. So like I said, I'm going to do another video, maybe even 2, going through a few more of these a little bit quicker, just so you can see some of them solved out in practice.